So today we're going to talk about different rules of doing integration. This is your warm-up, is this question. So when you're like differentiate y equals x to the 1 minus x is my warm-up. So if you want to put pause and then try it yourself before you go and see me, that'd be great. If you just want me to walk you through it, I'm going to walk you through it now. It would be y equals x to the 1 minus x. The issue is, of course, that you have an x in the base and an x in the variable and the exponent. So in order for me to get rid of that, we're going to take the natural log of both sides. So the natural log of y equals the natural log of x to the 1 minus x. And the reason that we did that is that then I could put the 1 minus x in front because it's a power. And now I can differentiate. Notice I didn't differentiate until now. The derivative of the natural log of y is 1 over y times dy dx, because that's not x. This is product rule. So the first times the derivative of the second plus the second times the derivative of the first. So now I have, and I'm solving for dy dx. If you wanted to, you could write this as 1 over y dy dx equaling, well, I could distribute, and I get 1 over x minus x plus 1 minus x. Could I distribute everything? So this is going to give you 1 over y dy dx equals 1 over x minus 2x plus 1. But I'm going to actually look at my answer choices. I don't think, yeah, that wasn't in there. Oh, but actually, it'll be okay. Here's why. There we go. Oh, you know what I didn't do? I did that wrong, and I didn't catch myself. I did this totally wrong. Okay, so this is the first times the derivative of second plus the second, because Miss Jero didn't do that correctly. The second times the derivative of the first. There we go. That's much better. I was like, there's something wrong. So I have, this isn't right. I'm fixing myself. So I distributed the 1 over x to that piece, and this gives you plus the natural log, or not plus the natural log of x. Wow, today it's going to be minus the natural log of x, which means that this, I'm just going to erase all of this. And you'll notice that I do have an answer that has a natural log of x in it, right? But it doesn't have two separate pieces. But however, I want you to notice that I could rewrite this piece as 1 minus x over x minus the natural log of x equals, and I'm going to write dy dx, but that meant that I had to get rid of this y. So I'm going to multiply both sides by y. So this is times y. But notice that there are no y's in this answer, but there is, we know that y is x to the 1 minus x. So my final answer can be 1 minus x over x minus the natural log of x times x to the 1 minus x, which is answer choice A. So if you got that right, good. This is all about manipulation, right? That's what this whole thing was about, is manipulation. And it's what we're going to do today when we're talking about integrations. We're going to talk about manipulation as well. All right. So the first one that I have, this is the first day of notes. And it's reminding ourselves of, if I have something, what do I look? How do I find the integral? Well, this one, okay, integration of 4 over x squared plus 9. So I'm going to rewrite this. I'm taking the 4 out because I can. 1 over, I'm going to write this as x squared plus 3 squared, because then maybe you'll recognize this as inverse trig. And it is the inverse of tangent. I'm going to write this as 1 over 3 squared plus x squared. You do not have to write this first line. You don't have to actually write. If you need it, write it. But that helps you to recognize things, write it. But if you don't, if you already recognize it, you don't have to write it. The 4 is going on the outside. I'm doing the inverse tangent x over a, but it's inverse tangent, which means you need 1 over a, and then plus 3, plus c. Or better yet, if you wanted to, I could write this as 4/3 inverse tangent of x over 3. You could write arctangent as well. We're totally fine with that. So that's my final answer. And that one was literally just, okay, 4 over x squared plus 9. I can rewrite that. How do I rewrite that? That's not new. Everyone okay with that? Hopefully you're good. I know I went a little fast. Sorry about that. Here comes b. B is the integration of 4x over x squared plus 9. That's different. This is not inverse tangent because of that x right there. Notice that x changes everything. This x right here changes everything. This is not inverse tangent. What it is u sub. Let u equal x squared plus 9. Then du is 2x dx. Which I almost have. Well, I do actually have, because this 4x could actually be written as 2 times 2x. If I wanted to, which means that I can integrate this, and I'm going to have a 2 still left over u du. And the reason why, ladies and gentlemen, is this 2x dx is du. So that's du, the 2 is still left over, and the u is on the bottom. I can integrate that. That integrates, that's natural log. So 2 natural log of the absolute value of u plus c, which gives you 2 the natural log of x squared plus 9 plus c. Absolute value needs to be there. However, just an FYI, for this problem, on this particular type of problem, I could actually get away with writing 2 natural log of the parentheses of x squared plus 9 plus c. And it would be acceptable as well. And let's see if I'm going to give you about 10 seconds to see if you can figure out why I would allow the parentheses instead of absolute value. Because in general, you have to have the absolute value. So if you've guessed why you would let parentheses, is because x squared plus 9 is always positive. There's no way for x squared plus 9 to be negative. So absolute value won't kick in. That's one reason why. Absolute value is general, what you want, and what you're gonna use. But if you gave me the blue, I would accept it, and you would get full credit for it. For this type of problem where the absolute values aren't gonna matter. All right, here we go. Part C. The letter C says 4x squared over x squared plus 9. And again, this is not an inverse tangent because of that x squared. It's not u sub because that's not going to help me. Anybody know what I got to do? If you think you know, put pause, do it, and then come back. If you need help, let the video run. If you need a hint, here's your hint. Long division. So, for those of you that need me to walk through it, oops, I wrote the wrong thing down first. It is going to be long division. So I'm going to do x squared plus 9 into 4x squared plus 0. In order for me to get that, I need a 4. So 4x squared plus 36. We are subtracting both pieces. So negative 36, which means this becomes 4 minus 36 over x squared plus 9. So I've simplified the black to the green, and now I can integrate this. The integration of 4 is just 4x. The integration of this is now inverse tangent. The 36 is going to hang outside. This is inverse tangent. X squared plus 9, that means it's not x over 3. But, because it's inverse tangent, you have to have 1 over a on the outside. And now I'm going to clean this up. 4x. 36 over 3 is 12. Inverse tangent or arc tangent of x over 3 plus c. So notice how one little variable can change everything. 3 problems. Literally, the difference is a single variable, and it changed how I did them. I could solve all of them, but 3 different problems. So a reminder of what these are. You know all these rules already, right? Integration, you can take a constant outside. You can separate them. Integration of du is just u. Integration of u to the nth is u to the n plus 1 over n plus 1. Du over u, natural log of absolute value of u, e to the u, e to the u. This is one that some of you forget. Right here, a to the u du is 1 over natural log of a times a to the u. And integration of sine is negative cosine. Integration of cosine is negative sine. Integration of cosine is positive sine, sorry. Integration of tangent, it is negative natural log of the absolute value of cosine of u. It is also the natural log of the absolute value of secant of u plus c. I tend to do this one. I tend to do the purple one, not the black one. Either one, that is one I would advise you to memorize. You can find it if you do sine u over cosine u and do u substitution. That's how you get there, but you just memorize it. It's just easier. Same thing for integral of cotangent. We actually haven't done that one, but you can because it's literally u substitution again. I would memorize integration of secant and integration of cosecant. Notice you know one of them. The other one was very similar. Cosine has a negative. Cosecant has a negative. Always all the cos have all the negatives. Again, you know these two. Integration of secant squared is tangent. Integration of cosecant squared is negative cotangent. Same thing for the 16 and 17. 18 and 19 are a reminder of our arcsines and arctangents. 20 is that arcsecant one that we don't use very often, but it's there. So this is just a reminder of all the different tangent or integration rules that we have so far. So here we go. Here's my next example. All right, it says the integration of 6 over 6 e to the x plus 6. I want you to take a second and I want you to think about how you would do this. Okay, so if you look at this problem, you're like, I don't know how to do that one. I'm going to give you a hint. You need to do some manipulation. Okay? And so we're going to do manipulation similar to things that we've done before, where we're adding and subtracting things. And we're going to do that same thing here. And watch what happens when I'm going to add or subtract. This hasn't changed, but I'm going to add and subtract something on the top. I'm going to add e to the x and I'm going to subtract e to the x. And here's the reason that I'm going to do that. I'm allowed to do that. That's adding 0. But now that gives me pieces on the top that I can now separate. Because now I can physically separate 2 pieces. I have 3 pieces. I'm going to separate it into 2 separate fractions. I'm going to separate it into 6 plus e to the x over e to the x plus 6. And I'm going to separate it into negative e to the x over e to the x plus 6. And if you notice, I'm allowed to do that now. Now you'll notice this left-hand piece. This left-hand piece is going to give you 1 minus e to the x over e to the x plus 6. So I have no problem with the left-hand piece integrating that. The right-hand piece, but it's e to the x. So if you think about it, well, I'm going to do u substitution now. I'm going to say let u equal e to the x plus 6. Then du is just e to the x dx. Oh, wait, I have that. So, by the way, I'm going to do this 1 dx minus the integration of 1 over u du. I'm putting this in dx because that way I don't have to worry about changing it back. So I'm going to put it as dx. That way they're 2 separate integrations. I don't have to worry about dealing with that. This is just going to give you x minus, this is the natural log of the absolute value of u plus c. And then I'm going to have x minus the natural log of the absolute value of e to the x plus c. E to the x plus 6 plus c. So again, today is all about manipulation. What it's about. Can you recognize manipulation and recognition? Can you recognize what method you have to use? because we have a multitude of different methods, then you need to be able to recognize which method am I supposed to choose. So if you think about it, oh yeah, I'm going to do one more example and then we're going to think about these. You ready? All right. Got the wrong pen. Got the wrong pen. Huh. Well, this one, let's see what I can do. Because the issue is that this doesn't factor the way it is. The bottom doesn't factor. So I have the integration of 4 over 4x squared plus 4x plus 65. The bottom doesn't factor. So that's an issue. The top is a single piece, so that's an issue. What I'm going to do is I'm going to manipulate the bottom. Gonna manipulate the bottom. And here's how I'm going to manipulate the bottom. I'm going to rewrite this as just 4 parentheses x squared plus x plus 65. So what I've done is I've just factored out the 4 out of the first 2 pieces. Now, I didn't factor out of everything, so I cannot cancel these out. They're not allowed to be canceled out because I didn't factor it out of everything. However, what I can do is I am going to play completing the square game. Meaning I'm going to do completing the square. Here's how completing the square works. I have x squared plus x. Remember what you're doing is you're taking half of x, half of b, squaring it, and adding it to both sides. So I don't have a both sides. So I have this. I took half of b, which is 1, which is 1/2, squared that, which is 1/4, and I'm adding it and subtracting it. Because reminder, I'm going to care about this piece because this is my perfect square. Right? This, I'm going to distribute. I'm going to do this piece right here. So I have 4 over, I have 4 parentheses, and another inside parentheses. This is x plus 1/2 quantity squared minus 1/4. And I still have this plus 65. Well, I don't want all these parentheses and everything, so I'm going to get rid of some stuff. So here's what I'm going to do. I'm going to distribute this 4 to both pieces in the parentheses. So it's 4 parentheses x plus 1/2 quantity squared minus 1 plus 65. So notice what I've done is I've distributed this 4 to the parentheses and to the 1/4. I can combine those terms. So now I have 4 over 4 parentheses x plus 1/2 quantity squared minus or plus 64. Now these 3 pieces, I can factor a 4 out of the top and bottom, right? So for those who are like, huh? I'll factor a 4 out of the entire thing at the bottom. 64 divided by 4 is 16. Nope. 64 divided by 4 is not 16. 64 divided by 4 is, no, it is. It is 16. That's my brain today. 16. Now you'll notice, ladies and gentlemen, now these 2 cancel out. So now I have 1 over 1x plus 1/2 quantity squared plus 16 dx, or 1 over, I'm going to write this as 4 squared plus x plus 1/2 quantity squared dx. And ladies and gentlemen, if it's written like this, that's inverse tangent. Tan to the -1 of my u, which is x plus 1/2. The derivative of that is just 1, so that's fine. Over a, which was 4, plus c, and you need to have times 1 over a. And so there's my final answer. Look at that pretty answer. All right. Everyone okay with that? So here comes the next one. So these, I actually have 3 of them here that I want you to try. And I have 3 answer choices for you as well. So the first one says dy dx equals x over the square root of x squared plus 1. The second one says x over x squared plus 1. And the third one says x cosine of x squared plus 1. What I'd love for you to do is to hit pause, and I'd like you to try all 3 of these, and then come back and hit OK. And so you can see me work out all of them or check your answers. I'll put the answers at the bottom so that you can see them. But I would highly recommend that you just hit pause, try them, and then come back to them. For those of you that want the answers, they are B for number 91, A for 92, and C for 94. We're going to do them all so you can see them for those of you that need them. We're going to do all of them right now. Give me 1 second to get to a new page. Slide the space. Oops. So if I'm doing this one, it is u substitution for this one. So we're going to say let u equal x squared plus 1. Then du is 2x dx. I don't have the 2, so I'm dividing by 2. So I have 1/2, because again, what am I doing but integrating both sides, right? That's what I'm trying to do. So I have 1/2 times the integration of 1 over the square root of u du, or that's the same thing as 1/2 times the integration of u to the negative 1/2 du. And so when I integrate that, the 1/2 hangs out. This becomes u to the positive 1/2 times 2, because it's dividing by 1/2, and then plus c. These cancel out. I'm left with the square root of x squared plus 1 plus c. Here's b. All right, to do the next one, 92. I'm going to come down here. If you'll notice that this one also is a u substitution, because again, also I'm finding the original function. So I need to do this. And I'm finding the antiderivative, so the original function. And so I'm going to say let u equal x squared plus 1. And then du is 2x dx. A lot of you may have thought for this one that it was inverse tangent. I noticed that that's an answer choice. The issue is this x on top. If this x on top wasn't there, it would be inverse tangent. It would be arctangent. But that x on top makes it not that. So I'm going to have a 1/2 on the outside. I'm going to have 1 over u du. The integration of 1 over u is the natural log of the absolute value of u plus c. Or better yet, 1/2 the natural log of the absolute value of x squared plus 1. Now, you'll notice, which is D, and you'll notice that that answer choice has a parentheses and not a bracket, a radical of the absolute value, because it has x squared plus 1 is always positive. Oops, I misspoke, because please look, that D is not the same thing that I have written. So it is not D, because that doesn't allow the 1/2. So the question is, oh, there's not one that looks like that. However, there actually is, because if you look at this problem and you look at A, please note that A and my green are the exact same thing. However, because what does 1/2 mean? I can put that as the power. And again, we've already established it doesn't have to be absolute value because x squared plus 1 is always positive. And if it's the power, I can write that as the square root of x squared plus 1. So again, manipulation so that my answer looks like what the answer choices are. All right, so there's one more. We're going to do number 94, and I'm coming back over to this one to do it. And that's this one right here, going down here. Actually, I'm going to put it back. So we're going down here. I'm going to do it down here. And again, I've got to use substitution again. So I'm going to say let u equal x squared plus 1, because again, I want to integrate so that I get the original function. And so du is 2x dx. So again, I'm going to have the 1/2 on the outside. The x is right here, so we're good on that piece. So it becomes cosine of u du. And the integration of cosine is sine, 1/2 sine of u plus c. And so my final answer is 1/2 sine of x squared plus 1 plus c. And that answer is C. And it looks just like mine. All right, so a reminder of what we have, the things that we can do. Most commonly, what you're going to see on the AP exam is separating the numerator into two separate pieces, expanding the numerator, so foiling or whatever you need to do, and using trig identities. Now, whether those are inverse trig identities or regular trig identities, they're both there. So here's something to help you remember called repeated. R for rational, the log rules, like log form. Taking the natural log of both sides. Expanding, so writing things out all the way, so foiling out. The power rule, you know that one. The exponentials. Algebra, factoring or separating the numerator. T for trigonometric substitution. I for inverse trig functions. And T for trig identities. And so repeated is a way to help remember, but again, these are the most common ones. Separating the numerator, expanding the numerator, and using trig identities are the most common ones that you work on. And so now what I want you to do, and you'll notice that here's the examples of them. Expanding, here's my expansion. Separating the numerator. Completing the square goes with algebra stuff. Dividing, so you get out of having x squareds on top, or having so you're separating so you can use natural log form. Adding, subtracting to the numerator. So notice that this, again, then I can factor that. Trig identities, multiplying, dividing by conjugate. So your homework is what I want you to start on now. You have your homework on your assignment sheet. Don't forget to upload the notes. Thank you.